Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome back to the deep dive. Today we are moving from the theoretical to the intensely practical. We're strapping on our safety goggles and plunging right into the microscopic, high-pressure world of industrial biomanufacturing. Our mission is specific. We're dissecting what might be the single most challenging engineering phase in all of bioprocessing. I'm talking about the transition, that volatile boundary where the upstream fermentation, the USP, ends and the recovery equipment for downstream processing, or DSP, begins. If you're running a facility, you know this pain point. We're not talking about small lab batches. We're talking about moving thousands of liters of thick, nutrient-rich broth under pressure, all while trying to maintain what should be a completely validated sterile boundary. So why is this moment just a simple act of moving the liquid? Why is it the source of so many headaches?
It's because industrial success, or failure, so often hinges right at that junction. What's fascinating here is that historically, facilities treated broth transfer as a simple logistics problem.
Right, just open a valve, turn on a pump, move the product.
Exactly. But the industry is now recognizing that you have to treat broth transfer and intermediate handling not as simple piping, but as sterility critical unit operations. They have their own measurable readiness criteria, completely separate from the performance of the fermenter itself.
So we can't just assume sterility because the fermentation went well?
No, absolutely not. The central insight we pulled from the source material is this. Post-fermentation sterility must be viewed as a time-dependent engineering performance variable. It's not a simple binary sterile or not sterile attribute.
What does that mean in practice?
It means a batch that is perfectly sterile at the start of the transfer might become compromised 2 hours later purely because of mechanical factors.
That's a really crucial framing. And how does that concept play out mechanically?
Because that transition point is defined by, well, the absolute worst combination of factors. You have relentless mechanical interfaces, the risk of human intervention, and the accumulated hygiene history of the facility.
All converging at once.
All converging on that critical boundary. You have physical fatigue, cleaning compromises, and sudden pressure changes. Time and wear are constantly working against you.
Okay, let's unpack the first big engineering headache then. The sheer architecture of the transfer system. At the lab scale, it's easy, right? Short lines, immediate processing. But manufacturing scale means extended piping networks, countless valves, pumps, heat exchangers, filters. The complexity is just mind-boggling, and every single one of those components is a failure mode waiting to happen.
Yeah.
And when we talk about this architecture, a huge variable is pressure profiles. In simple terms, how does the pressure you use to push this broth become a direct determinant of whether the batch stays clean?
That's where the paradox lies. You need high pressure to move a thick, viscous, high solids broth efficiently, but, well, rapid or high pressurization stresses the system in some really dangerous ways.
So?
Think about the mechanical seals and gaskets that hold the pipes together. They're often made of elastomers, a type of rubber. Rapid pressurization can physically distort those components, however subtly. And that momentary distortion creates what we call transient microleak pathways.
So tiny openings.
Microscopic openings at the gasketed joints that allow non-sterile air or liquid from the surrounding environment to get in. It's a physical breach driven by mechanical force.
So you risk sucking non-sterile air in because you push too hard. That sounds completely counterintuitive.
It is, which is why engineering that transfer profile is so critical. If you pull a vacuum or have a sudden pressure drop in a compromised area, you risk ingress. But the alternative is just as bad.
What's your?
Insufficient pressure. If you don't push hard enough, you prolong the transfer time. And time is the enemy here. Longer transfers mean more exposure to degradation variables like residual metabolism, temperature drift.
And it gives any contaminants on the pipe walls more time to grow.
Exactly, maximizing the chance for growth. So the engineering sweet spot is agonizingly narrow. You need enough pressure to move the volume quickly, but not so much that you mechanically fatigue the system. And you also have to worry about shear stress. Right?
Of course.
Absolutely. You have to minimize shear or lysis risk, especially with those high solids broths. If you damage the cells during transfer, they can release damaging intracellular components like proteases into the broth.
And those proteases just chew up your product.
They degrade your product. A mechanical handling problem becomes a massive yield loss problem for the downstream recovery team. It's a balance of three competing variables: mechanical integrity, time, and shear risk.
Let's move from pressure to geometry. If pressure is the force that breaks the boundary, the sheer physical complexity of the piping provides the weak spots. You call them interface complexity and hidden dead legs. So every single connection point, every flange, every valve, every weld is a place where sterility lives or dies based entirely on how well it was cleaned and sterilized beforehand.
And this is where operational drift creates enormous hidden risks. See, industrial facilities don't just spring up overnight, they evolve. A new sensor is added here, a new bypass loop is installed there, a temporary hose connection becomes permanent, and every one of those incremental upgrades can inadvertently create a local dead space, a short section of pipe that never achieves sufficient flow to drain completely or, more importantly, get adequate steam contact during sterilization.
You've essentially built a little contamination niche right into your validated sterile pathway.
Precisely. You've unknowingly built a persistent failure point into your architecture that remains invisible to standard checks. It's clean on paper, but thermodynamically, it's a cold spot or a residue collector.
That connects directly to the material running through those pipes. The broth characteristics themselves must play a huge role.
They absolutely do. When we talk about high viscosity or organisms with a filamentous morphology, meaning they grow in long strings, these characteristics aren't just logistical annoyances. They increase the required transfer pressure, which brings back that microleak risk we just discussed, and they dramatically elevate the risk of fouling.
And fouling isn't just about throughput, is it?
No, it's catastrophic for sterility. When broth residues stick to the inner pipe walls, they create insulating layers. These layers physically reduce the effectiveness of chemical cleaning during CIP, and, critically, they impede steam contact during CIP. Steam just cannot penetrate that insulating residue layer.
So you think you've sterilized the equipment, but really you've just baked the outside of a microbial cookie.
That's a great way to put it. It turns what started as a simple performance drag, slightly reduced flow into a much deeper sterility reservoir problem. That residue niche resists decontamination and acts as a hidden source that can seed subsequent batches.
That's a powerful distinction. Let's look at that industrial example from the sources, the high cell density one, because it shows how this problem can masquerade as something else entirely. So they were running an enzyme process, and they noticed downstream filter fouling was getting progressively worse. They assumed it was the DSP filters.
The obvious culprit.
Right. Maybe they needed more filter area, maybe the pretreatment was failing, but when they really dug in, the root cause was discovered right at the USP-DSP interface. Residue accumulation and incomplete cleaning of an upstream valve cavity near the fermenter outlet.
And the plant wasted time and money fighting a symptom. They focused on filter replacement downstream, but the true driver, the progressive introduction of bioburden, was a hidden residue niche right at that mechanical boundary. It was an interface problem that completely masqueraded as DSP inefficiency.
They were treating the fever instead of the infection. Speaking of boundaries, let's talk about closed transfer systems. We assume closed means safe because you've eliminated environmental exposure. But you mentioned earlier that boundary integrity is time-dependent. Does the definition of the sterile boundary actually shift during transfer?
It absolutely expands. A closed system prevents air contamination, yes, but it doesn't guarantee the integrity of its physical components. What often gets overlooked is that the sterile boundary physically expands to include all the inline equipment necessary for the move.
Like the pumps and heat exchangers.
The pumps, the external heat exchangers, the flow meters, all the associated piping. Suddenly, your small fermenter system becomes this massive, complex, sterile network that has to be maintained as one unit.
And the most heavily scrutinized component in that network is usually the filter itself.
Filters are essential barriers, but they introduce so much complexity. They cause pressure drop, they're prone to fouling, and their integrity can be compromised by the very act of using them.
So what's the common failure point there?
The major industry weakness is incomplete integrity assurance. We test pre-use to ensure the filter is intact. But if mechanical stress or fouling causes damage in process, a pin will tear, for instance, and the operator skips the post-use test, that crucial damage goes completely undetected.
Until the product fails QC down the line.
Exactly.
Now here is where the dynamism of the transfer process becomes so important. This concept of transient failures, especially valve sequencing errors. When a human or an automation system makes a mistake, it creates a momentary pressure fluctuation. How severe can that small momentary error really be?
It can be catastrophic. Even a fraction of a second of a sequencing error can create a momentary backflow or pressure reversal. And that's all the time you need to draw a non-sterile material, maybe residual liquid from a nearby drain, or non-sterile air from an unprotected vent back into the sterile stream.
So if a gasket is already a bit fatigued, a valve sequencing error is the trigger that pulls the contaminant across that weak barrier.
Precisely. And these events are often nearly invisible. They might be so brief that routine, slow-trending data systems won't even capture them. You'd need high-resolution monitoring to see it. But their sterility impact is immediate and severe, because even a momentary breach can seed an entire downstream hold tank.
This just emphasizes the need for dynamic evaluation, not static assurance. Remember that chilling example from the sources. A closed transfer line that passed all its static pressure tests. It was perfectly sterile when sitting idle. But it became non-sterile during the transfer because the constant pressure cycling caused microleaks at a fatigued gasket. The integrity changed under stress, and that seeded the hold tank, resulting in a batch failure days later.
That's the key takeaway of this entire section. Integrity assurance has to account for the mechanical stresses of operation, not just the static pre-use condition.
Okay, let's follow the broth. It gets past the transfer line and into the intermediate hold vessels, the surge tanks. These are often used as simple buffers, but they seem to occupy this ambiguous sterility category. Why is that?
Because they often straddle the line. They're not the fermenter, which is strictly sterile, and they're not always the final product tank, which has its own controls. They get treated as passive buffers, and that ambiguity is lethal because operational practices always drift towards the easiest path when sterility status isn't explicitly defined.
And that ambiguity creates systemic risk.
Absolutely. This raises a critical point about hygienic design. Surge tanks must be designed for perfect cleanability and complete drainability. If you leave residual films or solids, they become these rich nutrient sources, driving biofilm formation.
So if a tank can't be reliably cleaned and sterilized,
Then it must be explicitly designated as controlled bioburden equipment with strict operational limits. It cannot be implicitly assumed to be sterile by association with the fermenter.
and hold duration becomes a huge factor because any contamination, however small, is now in thousands of liters of perfect growth media.
It's a race against time. Even trace contamination amplifies rapidly in that environment. Hold duration stops being just a scheduling decision, it becomes a sterility variable. The result is a skyrocketing impurity burden that quickly overwhelms your downstream clarification capacity.
Which brings us back to that ambiguity example. A plant was treating their harvest surge tank as sterile by association. What did they miss?
They missed something simple but critical. The surge tank's vent path and certain internal geometries weren't fully included in the SIP coverage validation, so the tank was perfectly sterile for short holds.
But not for long ones.
But during long holds, say, over a weekend, sporadic contamination crept in through that weak point, appearing way downstream as inexplicable filter plugging and yield loss. The system was only as sterile as its least sterilized component.
Let's talk about long-term hygiene. We rely on cleaning in place, or CIP, but that's generally assessed batch to batch. You argue that the true impact of CIP emerges across campaigns. What does that progressive degradation look like?
It's subtle, but it's devastating. Over time, progressive residue accumulation and biofilm risk begin to systematically erode your sterility margins. The equipment looks clean, the CIP metrics look compliant, but the surfaces are degrading.
And this is where the hidden enemy, biofilms, comes into play. If your steam in place, your SIP, is hitting the right temperature for the right time, why can't we just trust the data?
Because biofilms are protective matrices. They shelter embedded microorganisms from chemicals and, crucially, from heat during sterilization. Biofilms are notoriously poor conductors of heat. So this means your SIP can look compliant. You hit 121 degrees Celsius for the right duration in the bulk flow, while the actual temperature at the equipment surface beneath the biofilm is significantly lower.
So the organism survives the SIP, and your sterility performance secretly degrades.
Exactly. It's a classic case of compliance versus effectiveness. Then there is the unique complication of microbial fermentation, antifoam residues. We use antifoam to control foam in the fermenter, but these hydrophobic films are incredibly difficult to remove during CIP.
Why is that a sterility problem, rather than just a cosmetic one?
Because these films dramatically reduce wetting during the subsequent CIP cycle. If the surface isn't properly wetted, the mechanical scrubbing and the chemical contact of the cleaning agents are undermined. If CIP is compromised, the next SIP cycle becomes inherently less reliable. It's a perfect example of an upstream control aid inadvertently becoming a long-term cleaning and sterility variable.
So what does this all mean for the facility manager who sees increasing variability? You suggest sterility failures are rarely some catastrophic alarm, but rather a progressive sterility margin erosion.
That's right. The problem manifests as increased variability, sporadic low-level contamination, and drifting downstream performance, not an obvious catastrophic failure. The mechanisms are mechanical fatigue, degrading seals over time, residue accumulation creating those hidden niches, and geometry-driven persistence, where a dead leg continuously recedes the system.
So to combat that erosion, we need to shift from reactive monitoring to proactive control. What systems need to be in place?
We need robust control mechanisms. Readiness checklists, when they're properly designed and enforced, have to function as engineering control systems. They reduce the reliance on tacit knowledge, the one operator who just knows the right sequence, and enforce consistent, validated sequencing every single time. And effective checklists are far more than just signing boxes. They have to verify critical engineering statuses, confirmation of SAP completion, assurance of filter integrity, both pre- and post-use correct valve alignment confirmed electronically, and confirmation of complete drainage before the next cycle begins.
Let's talk about the cost, because this is the sneaky financial drain that gets missed. You mentioned that productivity loss from these post-fermentation failures is frequently misattributed to DSP inefficiency. Why is the money always spent in the wrong place?
Because management sees declining filter throughput and blames the downstream team for bad operating procedures, but the mechanistic link is clear. Low-level contamination introduced during transfer or holding increases the overall bioburden, which fundamentally alters the broth.
How does low-level contamination alter the broth?
It changes the rheology, how the fluid flows. Contaminants can produce exopolysaccharides, making the broth stickier and harder to filter. They can also accelerate fouling of the separation equipment, so DSP performance degrades rapidly, even if the DSP protocols haven't been touched.
So companies often focus corrective actions on DSP. They buy more filter area, they modify flocculants, which only provides partial, temporary relief.
Exactly. They are applying a highly visible, expensive solution to a problem originating in a hidden, small mechanical interface. The true driver remains upstream. The transfer architecture, the long-term cleaning effectiveness, and the boundary governance at that USP-DSP interface.
The final industrial example brings this home perfectly. A facility invested heavily in increasing filtration capacity to address declining throughput. They spent millions to solve what they thought was a DSP problem.
And that investment yielded only marginal gains. Stabilization only occurred after they realized the underlying issue was a progressively fouling harvest transfer line with a persistent, low-flow residue niche. They had to redesign the line for better drainability and update the CIP coverage. They finally solved the mechanical integrity issue that was masquerading as a capacity constraint.
So to synthesize what we've discussed, sterility assurance at this interface is not a passive state. It is an active engineering challenge.
It forms the structural backbone that protects all of your upstream productivity. Defining that sterile boundary is crucial, and facilities have to accept that this boundary expands dynamically beyond the fermenter itself to include pumps, heat exchangers, and surge tanks.
That brings us to our final takeaway for you, the listener. Industrial reliability really hinges on three things: rigorous CIP's IFIPE integration, explicit sterility designation of all intermediate vessels, no more sterile by association, and extreme vigilance against that progressive erosion of sterility margins caused by hidden variables like mechanical fatigue and antifoam residues.
And here is a final provocative thought for you to explore, one of the biggest unresolved challenges in this space: finding predictive indicators of sterility margin erosion. Right now, we are reactive. We need validated methods to link subtle facility condition changes, things like evolving dead space detected by advanced imaging, tiny changes in gasket seal compression, or antifoam film accumulation to a probabilistic contamination risk before the batch is actually ruined. Now that's a deep dive for another day.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Urnala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.